All right, due to the fact that we are on an early out schedule today, I'm going to try to teach as much of lesson 57 as I can from the recorded portions and then cover what I can't cover on this video, possibly in class, and record that, make it a part 1, part 2. But where we're at is lesson 57, page 406. It's somewhat of a complex subject because we're talking about finding exponential growth and decay. So the first thing I mention in your book on page 406 is an increasing function. We're used to seeing these. It's a function whose output value increases as its input value increases. We see it rising from left to right. And that's how we read graphs, is from left to right and see what they do. Are they? We do that with slopes. Do they have a positive or negative slope as we read it from left to right? So we're used to seeing that. Exponential growth is a function that models situations where the quantity will increase by a percent for a given period. And so you're going to see it have this exponential growth as it goes. So it might start off small, but it's going to increase at a more and more rapid pace the further you move from left to right. And it's modeled by f of x, which we can replace with y, equals the constant times b to the power of x, where my constant is going to be a number that is greater than 0. It can be very, very small, but it's got to be greater than 0, which means it cannot be a negative number. And b is greater than 1. It can still be a fraction, but it has to be greater than 1. Anytime where I'm multiplying a constant by a number greater than 1, and I've got any kind of exponent, it is going to show exponential growth. Okay, so we can look at our formula that they give me, or my equation, and see what those numbers actually are and what the relation is to this information right here, okay, and determine if it's going to be an exponential growth or exponential decay based upon that. Okay, then we see decreasing functions are obviously functions whose output decreases as input increases. So if we're looking at a table of values, you would see your x values get smaller and smaller, that you would see your output y get smaller and smaller as your x values get bigger and bigger. Okay. Now an exponential in an increasing function, x gets bigger, y gets bigger. They get bigger together, and it falls. In a decreasing function, it's going to decrease from left to right. Okay. Exponential decay is a function used to model situations where the quantity always decreases by the same percent in a given time period, and it's modeled by this function where f of x or y still equals k, or my constant, times b to the power of x. Notice that this didn't change, but over here, my constant is now greater than 0. What was it before? Let's see. All right, we need to go back. Sorry. Oh. All right. In our exponential growth, we said b was greater than 1. I think I messed something up there. Hold on. Sorry about that. I accidentally copied and pasted some things around to the wrong place. All right, so in both models, k has to be greater than 0. So we see that for exponential growth. We see that for exponential decay. What is different is how b is affected here. Okay, b in exponential decay is going to be a number that is going to be less than 1 but greater than 0. So it has to be a positive fraction or decimal. Okay, if we go back to our exponential growth, it was a number greater than 1. So with decay, it's going to be a number less than 1, but greater still than 0. Okay? All right. All right, natural logarithms, you'll see this in a box on page 407. A natural logarithm of a positive x is the power to which e is raised to get x. That is, if e is taken to the power of y equals x, then y is called the natural logarithm of x. The abbreviation of that is y equals ln x, where ln is our natural log. And if I pull up our graphing calculator here, we're going to see that button right there underneath your log. is your natural log. And you'll notice right there, he's got an e to the x. If I hit second natural log, I get to e to the x. So we'll see that a little bit later. All right, if I can get my work here, then we'll start working out some questions. Got about 10 minutes, so hopefully I can answer a few of these before classes start. Okay, on question number 1, it says the function f of x equals 200 times 0.904 to the x. Now, we should notice that this is an exponential decay because b is less than 1 but greater than 0. In order going to be able to just plug this in our calculators, and I'll show you how. Okay, we want to know, hold on, we want to know where x is the time in years, models a declining feral cat population, predict a number of feral cats there will be in 6 years. So 6 is going to be my input. Okay. All right, so what I'm going to do is I'm going to go into the y function of my calculator, and I'm going to type in the equation that they give me. So I'm going to do 200, I got my y equals 200 times 0.904 to the x, okay, to the power of x. And I can hit graph, but due to the size of it, it may not actually show up. So we'll look, and thinking about it, let's see if I can change it to fit so we can actually kind of see it. It may not. Sometimes this graphing calculator doesn't. There we go. There we're seeing our exponential decay. Okay. Now, the second thing I'm going to do is I'm actually going to hit second graph, and it's going to give me a table of values. And they asked me to see how many feral cats there would be in 6 years, where x represented the number of years. In 6 years, I see that there's going to be 109.15 cats. All right. Notice that they start off with 200, and in 6 years, we're down to 109 feral cats. And that's what I like to hear, a declining population of cats. All right. 109 feral cats, and that's how we find that answer. Okay, so a lot of calculator usage here. All right, let's see, that was D. All right, let's look at number 2. Number of bacteria present in a culture after t minutes is given as B, or bacteria, equals 1,000 e to the k, or k is constant, if there are 2,412 bacteria present after 4 minutes, find K. One of the things I've written down here next to this question is example number 3. And I don't know, sometimes this is a little different in your book versus mine, but this is what I get for this. Is that taking this formula right here, for B, I'm going to start off with 2,412 bacteria. And that's going to equal 1,000 E to the k, and t is time in years, or sorry, t minutes, time in minutes. So I got 4 minutes there. All right, if I want to solve for this, okay, let's see, find k. I want to solve for k, which means I need to move everything else over. Well, this is 1,000 times e to the power of k times 4. So I'm going to divide by 1,000. Okay, and that's going to equal 2.412 equals e to the k, or sorry, e to the power of k to the 4th. Okay, at this point, what I want to do is that I know that my x, okay, or that my power, if I remember my natural log, let's go back and look at that note again. Okay, where I've got e to the y equals x. Okay, then y is the natural log of x. So I can figure that out this way, and I'll show you. Okay, let's go back to the question. Okay, so this is how I'd actually do this. Is that I'm going to take natural log of 2.412, and it's going to be equal to, okay, we're just going to find that, okay? We're going to find the natural log of 2.412, okay? Let's clear this out, second mode. Natural log of 2.412, okay? That gives me an answer of 0.88. So 0.88, okay, is equal here. All right, so what we're saying is that 0.88 equals the exponent k times 4. So I'm going to divide by 4 on both sides. So we're going to take 0.88 and divide it by 4. Okay, we'll just take that, divide by 4, and I get 0.22. So k equals 0.22. Now, let's go back and actually check this answer and see what we get. Okay, my k is 0.22. Let's see, I'm going to see if I can test this. Okay, we've got, because we want our answer to come out to the 2,412. So let's do 1,000, and let's do second ln, that's my e to the, okay, 0.22 times 4. And let's see if we get 2,412. 2,410.8, which would really give me 2,411. And because 0.22 is an approximation, it's getting me really, really close. So that's my ability there to test that answer. So k equals 0.22. Again, I would look at example number 3 for that question. Okay? All right, let's come down to number 3. Number 3 comes from example 1a. Example 1a. A savings account earns interest at an annual rate of 4% compounded semi-annually. If the account begins with a principal balance of $1,000, what is its value after 8 years? Okay, so I'm going to look at our book at example 1a because I believe they give me an equation to kind of go with here. All right, you see there, and use your examples in your book as much as you can. Okay, and this should be an exponential growth equation. And all right, notice it's compounded semi-annually. So let's take our amount here. So we got 1,000, and now we need our, and that's my constant, starting with 1,000. Now I need my b, okay, which is, in my case, we're doing 4% interest, okay. Okay, so I'm going to have some kids coming in here pretty soon. That's why I kind of stopped it. All right, so notice that it's 4% interest semi-annually, which means we're going to do this twice a year. Okay, so we've got 1, so we'll always multiply it by 1 because that's 100%, plus my rate divided by my time. So 0.04 divided by the rate at which it's compounded, which is semi-annually, so we'll divide that by 2. And this is after 8 years, okay, and so we're going to do the rate at which it's compounded, which is 2 times my time, which is 8 years. Okay, and that's my formula for that. Okay, so we can plug this in our calculator. Move it around. Okay, so we got 1,000 times 1 plus, I'm going to put this in parentheses so I get it separately, 0.04 divided by 2, close that parentheses, close the other parentheses, take that to the, I'm just going to go ahead and put this in as 16, and we get $1,372 $1,372.70. We'll round it up to 79 cents. So we'll have to stop right there for now, and we'll pick the rest up in class.